Hi, I'm Jim Anderton, Director of Content at Engineering.com. And ECM, electrochemical machining, is regarded by a lot of us as kind of a mystery. It's a black art. We know it exists. We know that it does some specific things. We're not sure what. Now I'm with Jonathan Chomis, and he's ECM Technology Specialist for the EMAG Group. And Jonathan, tell me about the process of ECM. What is it? What's it for? What are the applications?
Well, the basics are we remove material on a molecular level using electricity and salt water at the most basic level. Where it's used typically, and this is a good example here in the aircraft industry, hard to machine materials, high nickel, heat-resistant alloys that are very difficult to machine through normal 5-axis methods, we're using ECM. The best payoff there is there's no heat affected zone, there's no stresses, mechanical stresses, heat stresses put into the material, which then reduces the stress on the workpiece at the end of the process, makes it stronger, more lightweight.
Jonathan, we know from a scaling process, if you're a CNC machining guy, as I was, you get a sense of how much material you can take off, quote unquote, per pass, for example. How do you think about material removal rates with ECM?
Typically in a roughing scenario, we're removing anywhere from 5 to 7 millimeters per minute in a linear direction. That does not necessarily matter. It does not necessarily mean that the size of the feature matters. We always get the same material removal rate within reason. And then when we get down to a finishing, then it takes a little bit longer to remove that material, but we're able to achieve much higher quality surface finishes.
Okay, on traditional machining, of course, we can use feed speeds and change our cutting tool to switch from a roughing operation, for example, to finishing operation. How do you make that shift in ECM?
Well, we don't change our tool. We're able to use the same tool for roughing as we do for finishing. We may change the parameters of the electrolytic solution and how it's presented to the cutting gap, but more often than not, it's the same tool. So there's no changeover required between the roughing and finishing operation.
And what sort of finish can you achieve?
In the lab results, down to RA 0.5. Typically, we don't have to go that fine in the aerospace industry, so normally we fall well within our OEM requirements.
Okay, Jonathan, now we're standing in front of a blisk, and of course those who are not in the aerospace industry they intuitively know this, but retaining blades into a spinning hub at high temperatures and huge centrifugal forces has historically been a problem in the industry, and they developed fir tree fixation, all kinds of very expensive EDM-driven processes. Of course, the holy grail is make the whole thing in one piece, then it can't come off. What are we looking at here?
This is a good representation of a large blisk. Of course, this is just a sample, but the benefits here are, one, overall we're able to use less material in the base workpiece because we don't have to have, and when you compare this to a typical blisk that has a fir tree profile broached into it, typically you need to have more material to support that fir tree profile, which in turn makes the blisk much heavier. Here we're able to do it all in one part, no welding, roughing and finishing done in one setup. At the end of the day, it takes about 60% less time to do this particular blisk with ECM as compared to conventional 5-axis milling. So we get a huge cost savings in time, machine capacity, and also in weight savings as well.
Now, for individuals from a conventional machining side like I am, my perception was that ECM would be a slow process, a finishing-only process with very limited material removal rates and some question about control. So you're saying quite the opposite, that this actually is a faster way to achieve this net shape.
Absolutely. One of the big benefits, as I mentioned earlier, is regardless of the feature size, within reason, regardless of the feature size, it doesn't necessarily take us longer to cut a feature. We can remove a lot of material in a short amount of time. We've got essentially 3 different ways we cut. We cut either DC, which is full on, all power and axis movement to move that cathode and remove material. As we get down to maybe some slightly finer surface finishes, surface features, we'll use a pulse form, which is you'll see that more in EDM. We control on and off time, so we control the shape of the waveform. And then when we get down to PECM, we actually use an oscillation with the tools timed with that pulse form. So as the off time approaches, the cathodes will retract, we'll flush with clean electrolytic solution. As the pulse form turns on, the cathodes come in and we machine. We do this at a very high rate of speed, and those cycles are in milliseconds.
And what sort of materials are you working on? Obviously, we're going to be working with a high temperature superalloy, perhaps in this case down here, but what's the range of metals?
Really anything that can conduct electricity and does not have a high silicon content. So for instance, in the aerospace applications, we're cutting Inconel, Hastelloy, Waspaloy. Some other high heat and high stress applications, we're cutting Stellite. Really, again, anything that doesn't have a high silicon content. So some grades of aluminum are more difficult to machine than others. Some grades of carbide are more difficult to machine than others. And materials that don't fall into solution easily, platinum, for example, is another difficult to machine, if not impossible, with ECM.
Electrochemical machining, an option to consider if you need fast cycle times and a great surface finish.